Look up, gaze into the velvet expanse of the night sky. What do you see? Perhaps a handful of stars, or maybe thousands. Each one is a sun, like our own, but immensely far away. These pinpricks of light are just the beginning. They are our closest cosmic neighbors in an ocean of unimaginable scale. This universe does not just exist around us. We are a part of it. Its atoms are our atoms. Its story is our story. It invites us to explore, to question, to understand. The cosmos whispers its secrets to those who are willing to listen. The sheer size of it all can feel overwhelming. Billions of galaxies, each containing billions of stars. Our own Milky Way galaxy is but one island in this cosmic sea. And our sun, the star that gives us life, is just an average star, tucked away in a spiral arm. Yet from this small blue planet we dare to look out. We build tools. We launch probes. We extend our senses far beyond our physical reach. We are driven by an insatiable curiosity, a desire to know our place in this grand cosmic ballet. The invitation is open. The cosmos awaits. Where did it all come from, this vast universe with its galaxies, stars, and planets? For millennia, humanity has pondered this question. Today, science offers a compelling story. A story of a beginning. We call it the Big Bang. This was not an explosion in space like a firework. Instead, it was an explosion space. All the space, all the matter, and all the energy in the entire observable universe was once compressed into an unimaginably hot, dense state. A point smaller than an atom. Then it began to expand, rapidly. This expansion started about 13.8 billion years ago. In the first fractions of a second, the universe was a searing inferno. Too hot for atoms to form, too chaotic for light to shine freely. As it expanded, it cooled. Slowly, fundamental particles began to combine. Protons and neutrons formed. Then, after a few 100,000 years, the universe cooled enough for electrons to join with these nuclei. This formed the first atoms, mostly hydrogen and helium. At this moment, light was finally set free. It could travel unimpeded through space. We can still see the afterglow of this moment. It is called the cosmic microwave background radiation. It is the oldest light in the universe. Across the vast distances between stars, space is not entirely empty. It is filled with enormous clouds of gas and dust. These are called nebulae. Some are dark, obscuring the light from stars behind them. Others glow brilliantly, illuminated by nearby newborn stars. These nebulae are the cosmic nurseries. They are the birthplaces of stars. Within these colossal clouds, gravity begins its patient work. It pulls together denser regions of gas and dust. Slowly, over millions of years, these clumps grow larger and more compact. Their gravitational pull becomes stronger. As a clump collapses, its core heats up. The pressure inside increases dramatically. This dense, hot core is called a protostar. It is not yet a true star. It does not yet shine by its own nuclear fire, but it is on its way. The protostar continues to gather material from the surrounding nebula. Its temperature and pressure keep rising. Imagine squeezing a bicycle pump. The pump gets hot. The same principle applies here, but on an astronomical scale. The gravitational collapse converts potential energy into heat. This process continues for millions of years. Finally, a critical point is reached. Once a star is born, it enters a long period of stability. This is called the main sequence. Our sun is currently in its main sequence phase. During this time, the star steadily fuses hydrogen into helium in its core. The star's size, temperature, and brightness depend on its mass. More massive stars are hotter, brighter, and burn through their fuel much faster. Less massive stars are cooler, dimmer, and can live for trillions of years. Our sun, an average-sized star, will remain on the main sequence for about 10 billion years in total. It has about 5 billion years left. But stars do not live forever. Eventually, the hydrogen fuel in their core runs out. What happens next depends on the star's mass. For stars like our sun, the core begins to contract and heat up. The outer layers expand dramatically. The star becomes a red giant. It swells to hundreds of times its original size. It may even engulf its inner planets. The core becomes hot enough to start fusing helium into carbon and oxygen. This phase is relatively short-lived compared to the main sequence. Section 5. Gravity's ultimate triumph, the mystery of black holes. Imagine a star many times more massive than our sun. It lives a brilliant but short life. It fuses elements furiously in its core. Then it runs out of fuel. Its core collapses under its own immense gravity. If the core's mass is great enough, nothing can stop this collapse. not the pressure of electrons, not even the pressure of neutrons. Gravity, the fundamental force that shapes the universe, wins its ultimate victory. The core collapses indefinitely. It shrinks down to an infinitely small point, a point of infinite density. This is called a singularity. This is the heart of a black hole. Around this singularity is a boundary, a point of no return. This boundary is called the event horizon. Anything that crosses the event horizon can never escape. Not even light, the fastest thing in the universe. That is why we call them black holes. They absorb all light that falls into them. They reflect nothing. They are invisible to our eyes and telescopes in the traditional sense. Section 6. Time's elastic dance journeys near black holes. Albert Einstein revolutionized our understanding of gravity. His theory of general relativity tells us that gravity is not a force pulling objects together. Instead, gravity is the curvature of space-time. Space-time is the four-dimensional fabric of the universe, combining 3 dimensions of space and 1 of time. Massive objects like stars and planets warp this fabric. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip. Smaller objects, like marbles rolling nearby, will curve towards the bowling ball. This is how gravity works. Black holes take this warping of space-time to an extreme. Because a black hole crams an immense amount of mass into an incredibly small space, its gravity is extraordinarily strong. The curvature of space-time near a black hole is intense. This extreme curvature has profound effects, not just on the path of light, but also on the flow of time itself. According to Einstein, time is not absolute. It does not tick at the same rate for everyone, everywhere. Time is relative. It can be stretched or compressed by gravity and by motion. This effect is called time dilation. Section 7. Echoes in the Dark, the search for alien life. Are we alone in this vast cosmos? This is one of the most profound questions humanity can ask. For centuries we could only speculate, but today, we have the tools to begin a scientific search. We know that stars are numerous. We now know that planets orbiting other stars, called exoplanets, are also incredibly common. Our Kepler Space Telescope and TESS mission have discovered thousands of them. Some of these exoplanets orbit within their star's habitable zone. This is the region where temperatures could allow liquid water to exist on a planet's surface. Liquid water is crucial for life as we know it. The discovery of so many exoplanets has transformed the search for life. It suggests that the raw ingredients and conditions for life might be widespread throughout the galaxy. But finding a planet in the habitable zone is just the first step. We also need to look for biosignatures. These are chemical signs in a planet's atmosphere that could indicate the presence of life. For example, large amounts of oxygen, combined with methane, could be a strong hint. Future telescopes like the James Webb Space Telescope are designed to study the atmospheres of exoplanets. They will search for these telltale signs. The search continues, driven by the hope that we are not the only minds pondering the universe. Section 8. Listening for a Whisper, our cosmic conversation. If there are other intelligent civilizations out there, how might we find them? And how might they find us? For decades, dedicated scientists have been pointing radio telescopes towards the stars. They are listening for a pattern, a signal that stands out from the natural cosmic noise. The universe is full of radio waves from natural sources. Pulsars, quasars, and distant galaxies all emit radio energy. An artificial signal would need to be distinct, perhaps a narrow-band emission, or a repeating pattern that nature is unlikely to produce. This is the essence of radio SETI. The distances involved are staggering. Our galaxy, the Milky Way, is about 100,000 light-years across. This means even a signal traveling at the speed of light would take tens of thousands of years to cross it. If a civilization sent a message from the other side of the galaxy, it would take that long to reach us, and our reply would take just as long to return. This makes a two-way conversation incredibly slow, spanning generations. Yet the mere detection of a signal would be revolutionary. It would tell us that we are not alone, that intelligence has arisen elsewhere. Section 9. Beyond the Horizon. Dreaming of interstellar voyages, the stars beckon. For generations humans have looked to the heavens and dreamed of traveling to other worlds. The distances are the greatest challenge. Our fastest spacecraft would take tens of thousands of years to reach even the nearest star system, Proxima Centauri, which is just over 4 light-years away. A light-year is the distance light travels in 1 year. That is nearly 6 trillion miles, or 9.5 trillion kilometers. This scale is difficult to comprehend. It makes interstellar travel an enormous undertaking, far beyond our current capabilities. But humanity is a species that dreams. We are tool builders. We are explorers. Scientists and engineers are already thinking about future possibilities. Concepts like fusion rockets could significantly reduce travel times, perhaps to centuries or decades for nearby stars. Other, more exotic ideas are also being explored, at least theoretically. Warp drives, which would bend space-time to contract the distance in front of a ship and expand it behind, are a staple of science fiction. While the physics is highly speculative, it shows our ambition to overcome these vast distances. The future of interstellar travel is uncertain, but the dream persists.